NASA just found a mineral on Mars that takes millions of years of non-stop rainfall to create. Let me say that again. Rainfall on Mars. The planet we've been calling dead for half a century apparently had weather, not for a weekend, not for a century, but long enough to chemically transform rock the way Earth's tropics do. And when researchers started pulling at that thread, the whole story of Mars came apart. An ocean nobody predicted, organic molecules nobody can explain, lightning nobody knew was happening, and something beneath the Tharsis volcanic region that is still physically moving the planet. If you are new here, subscribe and get comfortable. Because tonight we're going to dismantle everything you were taught about the planet next door, and by the end, that little red dot in the night sky is never going to look the same again. Now, settle in and let's ease into it. Part 1. The impossible rock in Jezero crater. There is a white rock sitting on the surface of Mars right now that should not exist. It is small. It is pale. It looks, honestly, like the kind of thing you would walk right past on a gravel trail without thinking twice. But when NASA's Perseverance rover rolled up to it in Jezero crater and hit it with its SuperCam laser, a tool that can read the chemical fingerprint of a rock from 20 feet away, what came back stopped researchers mid-sentence. Kaolinite. Now, if that word means nothing to you, that is fine. It meant almost nothing to most people until about 2 years ago. But here is what you need to understand. Kaolinite is a clay mineral. On Earth, it forms in exactly one kind of environment. You need warm temperatures, you need chemically active water, and you need that water falling from the sky as rain, over and over and over again. Not for weeks, not for seasons, but for millions of years. It is the mineral signature of tropical weathering. When geologists find kaolinite in Earth's crust, they are not finding evidence of a puddle. They are finding the chemical remains of a rainforest. The Amazon basin is full of it. Southeast Asia is full of it. It shows up in places where rain has been hammering rock for so long that the original minerals have been chemically dismantled and rebuilt into something new. And Perseverance just found it on Mars. Let that land for a second. We're not talking about frozen water at the poles. We're not talking about the possibility that a river once flowed for a few thousand years through a canyon. We're talking about a mineral that requires a functioning rain cycle. Clouds forming, moisture rising, precipitation falling, water soaking into rock and reacting with it at a molecular level, and then doing that whole process again, millions of times, across millions of years. That is what kaolinite means. It is not a water signature, it is a weather signature, and this is the part that starts to unravel everything we thought we knew about the planet next door. Because for decades, the story of Mars has been pretty simple. Cold, dry, dead. Maybe it had some water once, a long time ago, probably underground, probably frozen, and probably gone now. The rovers were supposed to confirm that picture, fill in a few details, and help us plan where to land humans someday. Instead, Perseverance drove into Jezero crater and found evidence that it rained there. Not once, not from some freak event, but consistently over geological time. Think about what that requires. You cannot have rain without an atmosphere thick enough to hold moisture. You cannot have moisture cycling without significant atmospheric pressure, something Mars today does not have. Its atmosphere is less than 1% as thick as Earth's. You cannot have stable rainfall without thermal energy driving evaporation, which means you need surface temperatures warm enough to keep liquid water from freezing on contact with the ground. And you cannot sustain that for millions of years without some kind of greenhouse mechanism actively trapping heat against a sun that, 4 billion years ago, was roughly 30% dimmer than it is today. So you are already in trouble scientifically. Because the old models of early Mars said exactly the opposite. They said the atmosphere was too thin, the sun was too faint, and the temperatures were too low for any of this to work. And yet, here is the kaolinite sitting in the dirt, not caring about your climate models. Mars was not a puddle planet. It may have been a weather planet. And the difference between those two ideas is the difference between finding a cup of water in a desert and finding a rusted-out irrigation system buried under the sand. One is a curiosity. The other is evidence of a civilization of processes, clouds, pressure systems, wind patterns, evaporation cycles that we never imagined could have existed there. And if you're already rethinking what Mars looked like, good. Because we are not even close to done. That white rock in Jezero crater is just the first crack in a story that goes much, much further than rainfall. Because the crater it was found in, it is not just a hole in the ground, it is a geological archive, and what it is telling us changes the timeline of everything. Part 2, Jezero is not an accident. You might hear the name Jezero crater and think of it the way most people do, as a landing site. A spot NASA picked because the terrain was flat enough and the science looked promising enough to justify the risk. And that is true, as far as it goes. But Jezero was not chosen randomly, and what makes it extraordinary is not that Perseverance landed there. It is what was already there, waiting, long before any rover existed. Jezero is a river delta, not a metaphorical one, not a this kind of looks like it could have been shaped by water situation. It is a layered, structured, sediment-rich delta system that matches, almost feature for feature, the kinds of formations you see where rivers meet oceans on Earth. There are fan-shaped deposits spreading outward from a channel. There are layers of fine-grained sediment stacked on top of each other in the exact order you would expect from centuries of steady inflow. There are erosion patterns on the crater walls that indicate water did not just fill this basin once and sit there. Water flowed in, continuously, over geological time, and this is where the kaolinite finding from Part 1 stops being a single data point and starts becoming a pattern. Because if you have tropical-style weathering happening upstream, the kind of weathering that produces kaolinite, and you have a delta system downstream that shows sustained water flow, then you do not have two separate discoveries. You have a connected hydrological system. Rain falls, water collects, rivers form, rivers carry sediment, sediment builds deltas. And that cycle repeats, not for days, not for decades, but for long enough to lay down the kind of layered rock structures that Perseverance is now driving across. The flow patterns at Jezero are not chaotic. That is a key detail. When water hits a landscape in a sudden catastrophic flood, say, from a collapsing ice dam or a massive volcanic melt event, the deposits it leaves behind look very different from what steady, sustained flow creates. Flood deposits are jumbled. They mix large boulders with fine silt. They carve violently and leave irregular scour marks. What Jezero shows instead is the patient, organized geometry of a system that had time, braided channels, graded sediment layers, the kind of order that only emerges when water moves through a landscape predictably, year after year, era after era. Now, here is what the older Mars model struggled with. For a long time, the dominant explanation for any water features on Mars was catastrophic release, underground reservoirs bursting to the surface, flash floods carving channels, and then everything freezing again within centuries or less. That model fit the assumption of a cold, thin atmosphere Mars. It did not require rain. It did not require climate. It just required occasional violent plumbing failures beneath the surface. But Jezero does not look like a plumbing failure. Jezero looks like a watershed. And the problem with watersheds is that they demand climate. They demand evaporation feeding clouds, clouds moving across the planet, precipitation falling in highland regions, water collecting into streams, streams feeding rivers, and rivers delivering sediment to a basin terminus. That is not a local event. That is a planetary scale process. It means Mars, at least at one point in its history, was operating the way Earth operates, with a water cycle driven by atmospheric energy. The older models avoided this conclusion because they could not explain how Mars could sustain a thick atmosphere long enough for a cycle like that to establish itself. The Sun was faint. Mars is small. Its gravity is weaker, which means atmospheric molecules escape into space more easily. Every model that started with a thick early atmosphere eventually watched it bleed away in a few 100 million years, which sounds like a long time until you realise that kaolinite needs longer than that to form. But new orbital data and volcanic gas emission models are starting to change that picture. There is growing evidence that Mars may have had episodic atmospheric thickening, periods where volcanic outgassing, particularly from the enormous Tharsis volcanic province, pumped enough carbon dioxide, water vapour, and possibly hydrogen into the atmosphere to temporarily rebuild the greenhouse effect. Not permanently, not like Earth. But in long windows, potentially hundreds of millions of years at a stretch, where the atmosphere was thick enough and warm enough to sustain weather. That reframes Jezero completely. It is not just a fossil of a lake, it is a climate archive. It is a place where you can read the chemical and physical record of a planet that, at least for a while, behaved like a living world with active weather, circulating water, and geological processes operating in sync. And if that sounds like a big claim for one crater, hold that thought. Because Jezero is not the only place where this evidence is showing up. In fact, the water that fed this delta may have been flowing towards something much, much larger. Part 3. The first rewrite of Mars begins. Something was shifting in planetary science before the kaolinite discovery, before the delta mapping at Jezero, before any of the headline-grabbing results from Perseverance. It had been building quietly in conference papers and modelling workshops for over a decade. A growing discomfort with the way we told the story of Mars. The old version went like this. Mars formed roughly 4.5 billion years ago. It had a brief, possibly warm adolescence, maybe a few 100 million years where things were wet. Then the atmosphere stripped away, the surface froze, and Mars became the barren, rust-coloured husk we see today. End of story. Sad planet. Moving on. But the data was not cooperating with that narrative. Every new mission, every new mineral detection, every new crater analysis kept hinting that the wet period was not brief. It was not a blip, and it was not simple. The problem is something called the faint young sun paradox. 4 billion years ago, our sun was about 30% less luminous than it is now. That means less energy reaching every planet in the solar system, including Mars. Under current atmospheric models, Mars at that distance from a dimmer sun should have been frozen solid, an ice world from birth. And yet, there is the kaolinite. There are the deltas. There are the river channels visible from orbit, thousands of them, carved into terrain that should never have seen liquid water. So either the evidence is wrong, or the models are incomplete. And since you can hold kaolinite in your hand and run a spectral analysis on it, the evidence is not going anywhere. This has forced planetary scientists into a genuinely uncomfortable position. The mineral record says warm and wet. The atmospheric physics says cold and dry. Something has to give. And over the past several years, the candidates for that something have multiplied. Carbon dioxide alone probably cannot explain it. Even a thick carbon dioxide atmosphere on early Mars would struggle to raise surface temperatures above freezing under that faint young sun. So researchers have started looking at supplementary greenhouse gases, hydrogen, methane, sulfur dioxide, that could have worked alongside carbon dioxide to trap additional heat. Volcanic outgassing from Tharsis is one plausible source. Impacts from large asteroids could have temporarily injected heat and gas into the atmosphere. Even the behaviour of early Martian clouds, specifically high-altitude ice clouds that might have acted as a thermal blanket, has been modelled as a potential warming mechanism. None of these solutions are settled. That is the honest truth. There is no single model right now that perfectly reconciles the mineral evidence with the atmospheric physics. But what has changed, and changed significantly, is the direction of the conversation. 10 years ago, the default assumption was cold Mars, and warm-wet evidence was treated as an anomaly to be explained away. Today, the default is shifting. The evidence for sustained warm conditions is now strong enough that the burden of proof has moved to the cold Mars camp. They are the ones who have to explain why kaolinite is sitting in Jezero if it never rained. And here is where the story gets structurally important for everything that comes next. If early Mars really did have long climatic stability windows, periods of millions of years where temperatures were warm enough and the atmosphere was thick enough for rainfall, rivers, and standing bodies of water, then Mars was not just geologically interesting, it was pre-biologically interesting. Prebiotic chemistry, the kind that eventually led to life on Earth, requires a few things. It requires liquid water, it requires organic molecules, it requires energy, and critically it requires time, not a flash flood, not a weekend of warmth, but sustained, stable conditions where chemistry can build complexity without being frozen or boiled or blasted apart every few centuries. Mars, in this revised picture, may have had exactly that. Not a paradise, not a copy of Earth, but something more like Earth's Archean era, the period roughly 3.5 to 4 billion years ago when our own planet was still mostly ocean, mostly volcanic, and mostly devoid of complex life, but where the chemistry of life was already beginning to assemble in shallow water and hydrothermal vents. The comparison is not perfect, but it does not need to be, because the question is no longer whether Mars was ever habitable. The evidence has moved past that. The question is how habitable, for how long, and what happened as a result. And that question becomes much harder to ignore when you stop looking at individual craters and start looking at the planet as a whole. Because the rivers that carved Jazero's delta did not just appear out of nowhere. They were feeding into something, and recent evidence suggests that something was an ocean large enough to swallow the entire Arctic. Part 4. The Arctic-sized ocean nobody expected. Here is a number that is going to sit with you for a while. 14 million square kilometres. That is the estimated surface area of an ancient ocean that may have once covered a significant portion of Mars's northern hemisphere. For context, the Arctic Ocean, the one that sits on top of our own planet, the one that holds enough water to fill roughly 4.8 million cubic miles of space, the one you can see from orbit as a white-blue cap over the North Pole, covers about 14.06 million square kilometres. So when we say Mars may have had an ocean, we're not talking about a large lake. We're talking about a body of water roughly the size of the Arctic. That number comes from a study based on delta mapping and elevation analysis published in 2026, focused on geological features around the Val Marineris region and across the northern lowlands of Mars. What researchers found was a consistent elevation band, roughly between negative 3,650 metres and negative 3,750 metres below the Martian datum, which is Mars's version of sea level, where geological features abruptly change character. Below that line you see smooth, fine-grained sediment deposits. Above it you see rougher, eroded terrain with river channels cutting downhill. That transition line appears not just in one location, but across an entire hemisphere, stretching thousands of kilometres. That is what a shoreline looks like, not from up close where you would see waves lapping at sand, but from orbit, across geological time, where the evidence is written in the difference between what water touched and what it did not. And this connects directly back to the rainfall story we started in Jezero. Because an ocean does not just appear, it does not fill itself. Something has to deliver the water, and something has to keep delivering it, or the ocean evaporates and disappears. On Earth, that mechanism is the hydrological cycle. Water evaporates from the ocean surface, rises into the atmosphere, condenses into clouds, moves across continents, falls as rain, collects into rivers, and flows back to the ocean. It is a loop. And the evidence from Jezero, the kaolinite, the delta structures, the sustained river flow, now looks less like an isolated curiosity, and more like one piece of exactly that kind of loop operating on Mars. The river systems that fed into the northern lowlands were not short. Orbital mapping has identified channel networks stretching hundreds of kilometres from highland regions down into the low-elevation basin where the ocean would have sat. These channels show the same signs of sustained, non-catastrophic flow that Jezero's delta shows: graded sediment deposits, consistent channel widths, branching tributary patterns. These are not flood scars, these are drainage networks. the kind of systems that form when water is being delivered to high ground regularly enough and in large enough quantities to maintain permanent rivers. The sediment deposition patterns at the margins of the northern basin tell a similar story. Instead of the chaotic, jumbled deposits you would expect from a single catastrophic filling event, like an underground aquifer blowing out and flooding the lowlands in one enormous pulse, what researchers see is layered, organized sediment that accumulated gradually. It resembles what you see on Earth at passive continental margins, where the ocean meets a slowly eroding coastline, and sediment builds up in predictable stratified layers over millions of years. So you have an ocean, you have rivers feeding it, you have rainfall generating the river flow, and you have sediment records suggesting the whole system was stable over geological time. That is not a transient feature. That is a hydrosphere. And a hydrosphere of that scale requires something Mars is not supposed to have: an active, self-sustaining climate system with atmospheric circulation, thermal energy distribution, and a functioning water cycle. The dead planet keeps getting less dead, and the shoreline of that ancient ocean is about to tell us even more. Part 5. Mars had coastlines, not puddles. One ocean at one elevation would be compelling. But what makes the Martian ocean hypothesis genuinely difficult to dismiss is that there is not just one shoreline, there are several. Delta formations across the northern lowlands appear at multiple elevation levels, suggesting that the ocean's surface rose and fell over time, just as Earth's oceans have risen and fallen across ice ages and warm periods. This is not what you would expect from a single flood event that filled a basin and then froze. This is what you would expect from a body of water that was part of an active, changing climate system, one where the balance between evaporation, precipitation, and ice formation shifted over centuries and millennia. At some of these delta sites, researchers have identified features that go beyond simple water presence. There are sediment fans, the wide, flat deposits that form where a river slows down as it enters a larger body of water and drops its sediment load in a spreading arc. There are braided river patterns upstream of the fans, where channels split and merge repeatedly, a flow geometry that indicates high sediment loads and sustained discharge. And at some locations along the proposed shoreline, there are features that appear to be wave-modified deposits, sediment that has been reworked and redistributed not by flowing water, but by standing water with surface waves driven by wind. That last detail matters more than it might seem. Wind-driven waves require two things: a body of water large enough and open enough to develop surface chop, and an atmosphere with enough density and wind speed to push that water around. Modern Mars has an atmosphere so thin that even its strongest winds, which can reach speeds of nearly 100 km per hour during dust storms, exert almost no physical force. You could stand in a Martian hurricane and barely feel it. But an ancient Mars with a thicker atmosphere, the kind required to sustain rainfall in an ocean, would have had meaningful wind interaction with surface water, and that is what these deposits appear to record. So the picture emerging is not one of a static, frozen ocean locked under ice. It is a dynamic, wind-interacting, shore-modifying, actively maintained body of water that persisted long enough to leave geological evidence at multiple elevation levels across an entire hemisphere of the planet. This feeds back into the central question in a way that makes it much harder to sidestep. If Mars had an ocean that behaved like a real ocean, with shorelines, wave action, inflow rivers, and changing water levels, then Mars had a climate system. Not a residual one, not a dying one, a functional one, with precipitation zones, temperature gradients, and atmospheric circulation patterns driving weather across the planet. Some researchers have begun tentatively reconstructing what that climate zoning might have looked like. Polar regions with ice caps, we know those existed because we can see their remnants today. Mid-latitude zones with river systems draining toward the Northern Ocean, and potentially equatorial regions with higher temperatures and more direct rainfall, the kind of zones where kaolinite-forming weathering would be most intense. This is speculative, it is model-dependent. But it is no longer fringe. The physical evidence now requires this kind of thinking. Mars was not uniform. It was regionally dynamic. It had geography that mattered: highlands and lowlands, wet zones and dry zones, coastlines and interiors. It had, in a word, a planet's worth of complexity. And the fact that all of this apparently existed under a sun 30% dimmer than today's raises a question that has been tearing planetary science apart for years. How? How did any of this work? Part 6. The Forgotten Climate Model War. There is a fight happening in planetary science that most people have never heard of. It does not make headlines. It does not involve dramatic press conferences or viral images from rovers, but it is one of the most consequential debates in the field, because its outcome determines whether everything we just discussed, the rain, the rivers, the ocean, is a coherent story or a collection of contradictions. The fight is between two camps. On one side, you have the cold early Mars model. This has been the dominant framework for decades. It says that early Mars was, on average, below freezing. Any liquid water that appeared on the surface was temporary, released by impacts, volcanic eruptions, or underground aquifer breaches, and quickly lost to freezing or evaporation into a thin atmosphere. In this model, the river channels and deltas are real, but they are the products of brief, violent events, not sustained climate. The ocean, if it existed at all, was ice-covered and short-lived. On the other side, you have the warm early Mars model. This is the newer, more aggressive interpretation. It says that Mars had extended periods, possibly hundreds of millions of years, where surface temperatures were above freezing, the atmosphere was thick enough to sustain liquid water, and rainfall was a regular feature of the Martian environment. The kaolinite, the delta structures, the ocean shorelines, all of it fits naturally into this model without requiring special pleading. The problem is the Sun. 4 billion years ago, our Sun was a main sequence star in its adolescence, producing roughly 70% of its current energy output. At Mars's orbital distance, that translates to significantly less solar energy hitting the surface. Under standard atmospheric models, even a thick carbon dioxide atmosphere on early Mars would struggle to keep surface temperatures above the freezing point of water. Carbon dioxide is a greenhouse gas, but it has limits. At very high concentrations, it starts condensing into dry ice clouds that actually cool the planet by reflecting sunlight back into space. So you hit a ceiling, and that ceiling, in most models, sits below the temperature needed for sustained liquid water. This is the faint young sun problem, and it has haunted Mars science for 40 years. The evidence says warm and wet. The physics says cold and frozen. And the gap between those two conclusions has produced some of the most creative and contentious atmospheric modelling in modern science. The proposed solutions read like a wish list of greenhouse supplements. Hydrogen gas, possibly released by volcanic activity or produced by water rock interactions in the crust, could have acted as a powerful secondary greenhouse agent, absorbing wavelengths of infrared radiation that carbon dioxide misses. Methane, another potent greenhouse gas, could have been produced geologically, or, and this is the tantalizing part, biologically. Sulfur dioxide from volcanic eruptions could have contributed short-term warming pulses, and some models have explored the role of high-altitude water ice clouds, which, under certain conditions, could act as a thermal blanket, trapping heat near the surface while still allowing sunlight through. The Tharsis volcanic province, the largest volcanic region in the entire solar system, home to Olympus Mons and 3 other massive shield volcanoes, is the most frequently cited source for these atmospheric supplements. Tharsis was actively erupting for billions of years, and the sheer volume of gas it could have pumped into the Martian atmosphere is staggering. Some models estimate that Tharsis volcanism alone could have produced enough carbon dioxide and water vapour to temporarily thicken the atmosphere to something approaching Earth-like levels. But temporarily is the key word. The Cold Mars camp argues that even with volcanic outgassing, the atmosphere would not have stayed thick for long. Mars's weak gravity and lack of a global magnetic field meant that solar wind was constantly stripping molecules from the upper atmosphere. any gas Tharsis put up, the sun would eventually tear down. So at best you get episodic warm periods, windows of maybe a few million years where things got wet before the atmosphere collapsed again. The warm Mars camp counters that a few million years is more than enough. Kaolinite needs millions of years of continuous weathering, yes, but not necessarily tens of millions, and delta systems can build over timescales of hundreds of thousands to low millions of years. If Tharsis was episodically outgassing over a span of, say, 1 billion years, you could have multiple warm windows, long enough to build rivers, fill oceans, lay down deltas, and weather rocks into kaolinite, separated by cold, dry intervals. Neither side has won. The climate simulations still cannot perfectly reproduce the mineral and geological evidence using known atmospheric physics. Something is missing from the models. Maybe a gas we have not considered, maybe a cloud behavior we do not understand, maybe an energy source we have not identified. But what has changed is the weight of evidence. The cold Mars model used to be the safe bet. Today, it is the one playing defense, and that matters enormously for what comes next. Because if Mars really did have long stable windows of warmth, liquid water, and atmospheric activity, then those windows were not just hydrologically interesting, they were chemically interesting. And what Curiosity found in the mudstone at Gale Crater suggests that the chemistry happening in those ancient waters may have been far more complex than anyone expected. Part 7. The mudstone that should be empty. While Perseverance was rolling through Jezero, another rover on the other side of the planet had already found something that nobody quite knew what to do with. Curiosity has been operating inside Gale Crater since 2012. That is over 13 years on the surface of another planet, which, if you think about it, is longer than most people keep a car. Gale is a different kind of site from Jezero. It is an impact crater, yes, but what makes it special is not the crater itself. It is what is sitting in the middle of it. A massive central mound of layered sediment called Mount Sharp, rising roughly 5 kilometers from the crater floor, built up over billions of years as wind, water, and time deposited layer after layer of material and then carved most of it away again. Curiosity's job has been to slowly climb that mound, reading the geological history of Mars layer by layer, like turning pages in a book made of rock. Each layer represents a different era, a different climate, a different version of Mars, and the further Curiosity climbs, the younger the rock gets, which means the rover is essentially walking forward through time, and in one of those layers, a formation called the Cumberland Mudstone, laid down roughly 3 billion years ago, Curiosity's onboard laboratory, a miniaturized chemistry lab called SAM, short for Sample Analysis at Mars, detected something that changed the trajectory of the entire mission: organic molecules. Now, before you jump ahead, let me be precise about what that means and what it does not mean. Organic in chemistry does not mean biological, it means carbon-based. Organic molecules are simply molecules built on a carbon backbone, and they can form through entirely non-living processes. Meteorites carry them, volcanic vents produce them. Ultraviolet light hitting the right atmospheric gases can synthesize them. So finding organic molecules on Mars does not, by itself, mean life. But the specific molecules Curiosity found, and the amounts it found them in, are what made the scientific community sit up and pay very close attention. Specifically, Curiosity detected a suite of chain-length hydrocarbons: decane, undecane, and dodecane. Those are molecules with 10, 11, and 12 carbon atoms respectively, arranged in straight chains with hydrogen atoms attached. If you could zoom in and look at them, they would resemble tiny molecular caterpillars, simple, linear, orderly. On Earth, molecules like these are everywhere. They show up in petroleum, they show up in plant waxes, they show up in the waxy coatings of insect exoskeletons. They are found in the decay products of cell membranes, in the chemical residue left behind when biological material breaks down over time. They are, in a very real sense, the chemical fingerprint of life doing what life does, building structures out of carbon and then leaving those structures behind when the organism dies. On Mars, they were detected at concentrations of roughly tens of parts per billion. That sounds small. It is small. If you filled an Olympic swimming pool with Martian mudstone, the organic molecules Curiosity detected would amount to a few drops of liquid in that entire volume. But the context makes it significant, enormously significant, because these samples have not been sitting in a protective vault. They have been sitting on the surface of Mars for approximately 3 billion years, exposed to one of the harshest radiation environments in the solar system. And this is the part people miss when they hear parts per billion and shrug. Mars has no global magnetic field to deflect charged particles from the Sun and from deep space. Earth does. Our magnetosphere acts like a shield, redirecting most of the high-energy radiation that would otherwise slam into the surface. Mars lost that shield billions of years ago. It also has no ozone layer to block ultraviolet light. On Earth, our ozone layer absorbs the most damaging wavelengths of UV radiation before they reach the ground. On Mars, the full spectrum hits the surface unfiltered every single day. Every organic molecule on or near the surface is being slowly, relentlessly destroyed, pulled apart by cosmic radiation, shattered by particle bombardment, oxidized by UV-driven chemical reactions that turn complex molecules into simpler, less interesting fragments. The fact that anything survived at all is remarkable. 3 billion years of bombardment, and these molecules are still there, still detectable, still identifiable by chain length. That is not supposed to happen easily. And when researchers ran the radiation exposure backward, building models of how much organic material would have been destroyed over 3 billion years of continuous unshielded surface exposure, the numbers were striking. The calculation suggested that the original concentration, at the time these molecules were first buried in the mudstone, could have been orders of magnitude higher than what Curiosity measured. Not tens of parts per billion, possibly parts per million. That is a 1,000-fold increase. That is not a trace. That is not a smudge. That is a measurable, significant concentration of complex organic chemistry locked into an ancient rock on a planet 225 million kilometers from the nearest known biology. Let that number sit with you. 225 million kilometers. That is the average distance between Earth and Mars. The nearest known source of biology, us, our planet, our biosphere, is that far away. And yet, here are molecules that, on our world, are produced overwhelmingly by living systems, sitting in Martian rock at concentrations that, when corrected for 3 billion years of radiation damage, start to look genuinely difficult to explain without invoking something more interesting than random chemistry. The mudstone itself matters here, and it matters a lot. Mudstone is fine-grained sedimentary rock, formed from compacted silt and clay particles that settled out of standing or slow-moving water. Think of the bottom of a quiet lake, the kind of place where the water barely moves, where fine particles drift down through the water column like snow and accumulate in thin, even layers on the lakebed floor. Over time, those layers compact, dewater, and lithify into rock. And that rock turns out to be one of the best natural preservers of organic material on Earth, because the tiny grain size creates a dense, low permeability matrix that acts like a molecular prison, trapping whatever was in the water at the time of deposition and shielding it from oxygen, from circulating water, and critically, from radiation. The Cumberland Mudstone in Gale Crater appears to have formed in exactly that kind of environment. Quiet, low-energy water, fine sediment settling undisturbed, an ancient lake filling the floor of a crater that itself was created by an impact billions of years earlier. It is the kind of geological setting that, if you were designing a mission to look for preserved organic material on Mars, you would specifically target. And Curiosity drove right into it. So here is where we stand, and I want you to hold all of these threads at once for a moment, because the weight of this story is not in any single fact. It is in the accumulation. Mars had rainfall, the kind of sustained, long-duration tropical rainfall that produces kaolinite. a mineral that requires millions of years of chemical weathering to form. Mars had rivers, organised, persistent drainage networks that carried water and sediment across hundreds of kilometres of terrain. Mars had an ocean, a body of water roughly the size of the Arctic, with shorelines visible at consistent elevations across an entire hemisphere of the planet. And now, in the ancient lakebed sediment of a completely different crater, on the other side of the planet, we have organic molecules, the same class of hydrocarbons associated with biological processes on Earth, preserved in rock that formed in exactly the kind of quiet, water-rich environment where life's chemistry could have operated. Nobody is claiming this is proof of life. That needs to be said clearly, and I will keep saying it, because the gap between interesting chemistry and confirmed biology is enormous, and jumping across that gap without sufficient evidence has burned scientists before. But the coincidence is starting to accumulate weight. Each piece alone is ambiguous. Together they form a pattern that is getting harder and harder to dismiss as accidental. And the question researchers are now asking is not, did Mars have organic molecules? That question has been answered. The molecules are there. They are real. They are measured. The question is, where did they come from? Because the non-biological explanations, the ones that should be the default in good science, are having a harder and harder time keeping up. Part 8. Why this is scientifically explosive. Decane, undecane, dodecane. 10, 11, 12 carbon atoms. It sounds like a chemistry textbook nobody asked to read. But stay with me here, because the chain length of these molecules is the detail that keeps planetary scientists awake at night, and once you understand why, you will not be able to unsee it. Why does the chain length matter? Because in the known universe of abiotic chemistry, chemistry that happens without biology, without cells, without life of any kind, straight-chain hydrocarbons in this range are unusual, not impossible. Nobody's saying impossible, but unusual. And the distinction between unusual and impossible is exactly where this entire debate lives. It is the crack in the wall that keeps getting wider every time someone looks at it more closely. Abiotic sources of organic molecules on Mars have been thoroughly investigated. This is not a case of scientists seeing something strange and immediately jumping to the most exciting conclusion. The boring explanations were tested first. That is how science works. You try to kill your most interesting hypothesis before you let yourself believe it. And every plausible non-biological source has been put on the table and examined. Meteorites deliver organic material to Mars's surface constantly. This is not speculation, it is measured fact. The solar system is full of carbon-rich debris, and Mars, like Earth, gets pelted with it regularly. Carbonaceous chondrites, a common type of meteorite, contain an entire zoo of organic compounds, amino acids, carboxylic acids, aromatic hydrocarbons, and yes, some straight-chain hydrocarbons. If you picked up a carbonaceous chondrite and ran it through a mass spectrometer, you would find organic molecules. No biology required, just chemistry happening in space over billions of years. Hydrothermal systems offer another pathway. Volcanic vents where superheated water reacts with rock can produce organic molecules through a process called Fischer-Tropsch synthesis. The mechanism is straightforward. Carbon monoxide or carbon dioxide gets chained together with hydrogen on the surface of mineral catalysts, building up hydrocarbon molecules link by link, like adding beads to a string. This process is real. It happens on Earth today at mid-ocean ridges, and it almost certainly happened on early Mars, where volcanic activity was orders of magnitude more intense than anything on our planet today. And then there is atmospheric chemistry. Ultraviolet radiation hitting carbon dioxide and water vapor in the Martian atmosphere can crack those molecules apart and reassemble the fragments into simple organics, formaldehyde, methane, small hydrocarbons that drift down to the surface like invisible chemical rain. All of these sources are real. All of them have been documented, modelled and published in peer-reviewed journals, and none of them comfortably explains what curiosity found. The problem is threefold, and each fold makes the next one worse. First, the chain length. Meteoritic organics tend to be dominated by shorter carbon chains and more complex branch structures, molecules that look like tangled bushes rather than straight lines. When you analyse the organic content of a typical carbonaceous chondrite, you see a messy, diverse mixture that peaks at shorter chain lengths and drops off rapidly as the chains get longer. Fischer-Tropsch synthesis can produce longer chains, but it typically generates a broad, smooth distribution of chain lengths with a predictable mathematical fall-off, lots of short chains, fewer medium chains, very few long chains, following a pattern that looks like a ski slope on a graph. What Curiosity detected does not match either of those profiles. It found a concentration of specific chain-length alkanes, decane through dodecane, 10 through 12 carbons, at levels that stick out from what those abiotic pathways would predict. It is not that these molecules cannot form abiotically. It is that they should not form in this particular abundance pattern without something selecting for them, something organising the chemistry, something favouring these specific chain lengths over others. On Earth, we know what that something is: biology. Second, the preservation problem. These molecules survived 3 billion years of radiation bombardment. 3 billion years. That is a number so large it stops meaning anything unless you anchor it to something. 3 billion years ago, life on Earth was single-celled. Photosynthesis was just getting started. The atmosphere had barely any oxygen. Continents were unrecognizable. And these molecules were already buried in Martian rock, already being bombarded, already being degraded one molecular bond at a time by cosmic rays punching through the thin atmosphere and into the ground. The Cumberland mudstone provided protection. Its fine-grained structure acts as a partial radiation shield, but it is not impervious. The fact that these hydrocarbons are still detectable at tens of parts per billion after 3 billion years of slow molecular destruction implies that the original abundance at the time of burial was far, far higher. We talked about this in the last section, possibly parts per million, a 1,000-fold increase over what remains today. And that original abundance is difficult, genuinely, mathematically difficult, to produce through any known abiotic mechanism operating at the rates and scales expected on early Mars. Meteorite delivery is too diffuse. Fischer-Tropsch synthesis at Martian hydrothermal vents would need to be unrealistically productive. Atmospheric photochemistry produces the wrong molecules at the wrong concentrations. Every non-biological pathway you try to fit to the data requires stretching assumptions further than the data supports. Third, and this is the one that makes the hairs on the back of your neck stand up, the context. These molecules were not found in some random volcanic rock or loose surface dust, where they could have been deposited by any number of processes. They were found in a lakebed mudstone, in fine-grained sediment that settled to the bottom of a quiet ancient lake, in exactly the kind of environment where, on Earth, biological organic material accumulates, gets buried, and gets preserved. If you were designing an experiment to find biological signatures on Mars, if you sat down with a team of astrobiologists and geologists and said, "Where should we look, and what should we look for?" they would tell you to find a fine-grained sedimentary rock formed in a low-energy aqueous environment, and they would tell you to look for chain-length hydrocarbons consistent with lipid decay products. That is what you would design, and that is what Curiosity found. Not because anyone designed it that way, but because that is what was sitting in the rock. That does not prove biology. Context is not causation. But it does mean this discovery cannot be waved away as a random chemical curiosity found in an irrelevant geological setting. The molecules are right. The setting is right. The preservation story is right. Everything lines up in a way that, if this were Earth, nobody would even debate the origin. It would be biological, case closed, next paper. But this is not Earth, and that is the only thing keeping the debate open. On Earth, hydrocarbons in this chain-length range are overwhelmingly produced by one process: biological lipid breakdown. Cell membranes are built from fatty acids, long carbon chains with a chemical head group that allows them to self-assemble into the thin, flexible barriers that separate the inside of a cell from the outside world. Every living cell on Earth has them. When organisms die, those fatty acid chains break down. Enzymes and environmental chemistry snip off the head groups, and what remains are the carbon-hydrogen skeletons, straight-chain alkanes like decane, undecane, dodecane, and their longer and shorter relatives. The biochemical pathway is well understood, well documented, and operates in every environment on Earth where life exists and dies, from ocean floors to forest soils to the insides of your own digestive system. Microbial biofilms produce them. Waxy leaf coatings produce them. Algal mats in shallow water produce them. When any of these biological materials decay and get buried in fine-grained sediment at the bottom of a lake or ocean, you get exactly the molecular signature curiosity detected on Mars. Now, does that mean biology is the only possible explanation? No, and this is where intellectual honesty requires us to slow down and resist the gravitational pull of the most exciting answer. Mars is not Earth. Its mineralogy is different. Its radiation environment is different. Its atmospheric chemistry is different. It is entirely possible, genuinely, non-trivially possible, that some abiotic pathway exists on Mars that we simply have not identified yet. Some mineral-catalyzed reaction unique to Martian conditions, operating at Martian pressures and temperatures, using Martian feedstock chemicals, that can produce decane-range alkanes in the concentrations Curiosity observed. We cannot rule that out. We do not know enough about Martian geochemistry to rule that out. But here is the scientific reality of that position. It is possible that an unknown process exists that we have not discovered yet, is a weaker scientific statement than we have a known process that produces exactly this result, and it is called biology. One is speculation about what might be, the other is observation of what is. And when you are weighing two hypotheses, one grounded in documented reproducible biochemistry, and one grounded in the hope that an undiscovered reaction exists, the documented one carries more weight. Not conclusive weight, not case-closed weight, but more weight. The scientific community is handling this with appropriate caution, and they should be. The sample size is tiny, one formation, one crater, one rover's analytical instrument with known limitations and known quirks. SAM, the instrument that made the detection, works by heating rock samples in a tiny onboard oven and analysing the gases that come off. That process can sometimes create artifacts, new molecules generated by the heating itself, by reactions between the sample and the instrument's own materials, rather than molecules that were present in the original rock. Contamination from Earth, carried on the rover's own hardware despite extraordinary cleanliness protocols, remains another concern that has been painstakingly but imperfectly controlled for. So the honest summary, the one that a responsible scientist would give you at the end of a long conference talk, after all the caveats and all the error bars, is this. We have organic molecules on Mars. They are in the right geological setting. They are at concentrations that known abiotic sources struggle to explain. They match the chain-length profile of biological lipid decay products on Earth, and they survived 3 billion years of radiation exposure, which implies original concentrations even more difficult for abiotic models to produce. That is not proof. But it is a statistical anomaly that is getting harder and harder to wave away with each new analysis, and the language being used to describe it, in journal papers, in conference proceedings, in the careful, hedged sentences that scientists use when they know the world is listening, is starting to change. And that change in language, that quiet, almost invisible shift in how researchers talk about what Curiosity found, that might be the most important signal of all. Part 9. The quiet scientific language shift. There is a phrase that has started appearing in astrobiology literature over the past few years, and if you know what to listen for, it lands with unusual weight. The phrase is reasonable hypothesis of biological origin. At first glance, it sounds almost underwhelming, almost like bureaucratic language. But in science, especially in fields as cautious and conservative as astrobiology, that kind of phrasing is never accidental. It is carefully constructed, stress-tested, and softened to survive peer review. Researchers do not say, "We found life on Mars," unless they can prove it beyond extraordinary doubt. Instead, they adjust probability language in incremental steps. An reasonable hypothesis of biological origin is not a small step. It is a threshold shift. For decades, the default interpretation of organic molecules detected on Mars was simple. They are interesting, but ultimately abiotic by assumption. The standard phrasing in papers leaned heavily toward variations of consistent with non-biological processes, or does not require biological explanation. That distinction mattered. It placed biology in the category of unnecessary complexity. If a molecule could be explained without invoking life, then life was not needed in the model. In that framework, biology was not just unproven, it was structurally excluded unless absolutely unavoidable. That framing has not been officially overturned. No space agency has declared a reversal. NASA, ESA, and other institutions still maintain the conservative baseline. Extraordinary claims require extraordinary evidence, and life beyond Earth remains unconfirmed. But something important has changed underneath that surface-level caution. The language has begun to stretch. Now, in certain discussions of Martian organics, particularly in peer-reviewed literature analysing complex hydrocarbons, sedimentary preservation environments, and unexpected concentration levels, the phrasing is no longer just abiotic consistency. It is often followed by a second, more careful sentence, that a biological origin cannot be excluded, and in some cases, that it may represent a reasonable hypothesis. That shift matters more than it sounds like it should. Because science does not usually announce revolutions in loud declarations, it changes through vocabulary drift. Before any paradigm collapses, the language begins to loosen at the edges. What was once described as impossible becomes unlikely. What was unlikely becomes not ruled out. Not ruled out becomes plausible. And plausible, if the evidence continues to accumulate, eventually becomes reasonable. Each transition is small enough to survive institutional scrutiny. No single paper is revolutionary on its own, but collectively they shift the centre of gravity of an entire field, and that is exactly what is happening in astrobiology right now. The reason this particular phrase is seismic is not because it confirms life. It does not. It is seismic because it marks the point where biology stops being treated as an unnecessary explanation and starts being treated as a serious competing hypothesis. That is a fundamentally different scientific posture. It does not mean the conclusion has been reached. It means the boundary of acceptable interpretation has moved. To understand why this shift is happening, you have to look at what is accumulating on Mars, not as isolated findings, but as a system of overlapping evidence that is beginning to form a coherent picture. There is the mineral evidence first. Kaolinite deposits in Jezero crater, identified by NASA's Perseverance rover. On Earth, kaolinite forms through long-term chemical weathering in warm, wet environments, not transient wetting, not occasional meltwater, persistent rainfall, interacting with rock over extended periods of geological time. The implication is not just that Mars had water, but that it may have had a hydrological cycle capable of sustained rainfall and surface alteration. Then there is the geomorphology. River deltas preserved in multiple regions, particularly around Valles Marineris, suggest sustained inflow into a large standing body of water. These are not chaotic flood deposits. They are layered, structured sediment systems that on Earth form only in stable lake or ocean environments. Elevation mapping across these features suggests consistent shoreline levels, implying a massive ancient ocean, potentially covering much of the northern hemisphere. Individually, each of these lines of evidence is interpretable in multiple ways. Together they begin to reinforce each other. Rainfall feeds rivers. Rivers feed oceans. Oceans create sedimentary basins. Sedimentary basins preserve organic chemistry, which brings us to the third line of evidence, carbon chemistry itself. In mudstone samples from Gale Crater, the Curiosity rover has detected a suite of organic molecules, including decane, undecane, and dodecane, straight-chain hydrocarbons consisting of 10, 11, and 12 carbon atoms respectively. On Earth, molecules in this range are frequently associated with biological lipid breakdown products. They are not exclusive to life, but they are strongly enriched in biological systems compared to abiotic ones. The concentrations measured in Martian samples are low in absolute terms, parts per billion. But when researchers model radiation degradation over billions of years of surface exposure, they estimate that the original concentrations may have been significantly higher, potentially reaching parts per million levels. That is a range where biotic explanations become increasingly strained under known geochemical models. Meteorite delivery has been considered. Atmospheric synthesis has been modelled. Hydrothermal analogues have been tested. None fully reproduce the observed abundance and distribution patterns without introducing additional assumptions, which is where the language begins to shift again, not toward certainty, not toward confirmation, but toward something more uncomfortable, serious plausibility of biological origin under certain environmental conditions, and that is where the phrase reasonable hypothesis of biological origin begins to appear, not as a claim, but as an admission of intellectual space. Because at that point the problem is no longer whether organic molecules exist. They clearly do. The problem is whether their concentration, structure and preservation state can be fully explained without invoking biological chemistry in a world that, for a long time, may have had oceans, rainfall and long-term climate stability. That is the tension the field is now living inside. On one side, the data is accumulating into a picture of ancient Mars that looks disturbingly Earth-like. Stable hydrology, long-lived surface water, active sedimentary cycles, and complex organic chemistry preserved in protective mineral matrices. On the other side, the constraints are severe. We have only a handful of sample sites, no global subsurface access, and no laboratory-grade analysis performed directly on returned Martian material. And that last limitation is not just a technical detail, it is the central bottleneck of modern Mars science. The Mars Sample Return mission was designed to solve exactly this problem. Perseverance has been collecting and caching sealed sample tubes on the Martian surface, carefully selecting sediments that may contain preserved chemical and geological records from ancient environments. These samples are, in effect, time capsules from a world that no longer exists. The plan was to retrieve them, return them to Earth, and analyze them in laboratories capable of detecting biosignatures at molecular and isotopic resolutions far beyond rover instrumentation. That level of analysis could, in principle, distinguish between abiotic and biological origins with far greater confidence. But that mission has now been effectively halted due to escalating costs and engineering complexity. The sample tubes remain on Mars, sealed, catalogued and stationary, waiting for a retrieval system that may take decades to materialize, if it happens at all. In the meantime, an alternative pathway is emerging. China's Tianwen-3 mission is currently planned to return Martian samples independently in the early 2030s. If successful, it would represent the first direct laboratory analysis of Martian material on Earth. That would immediately transform the field, because it would replace indirect rover-based inference with high-precision geochemical measurement. In other words, it could resolve the question that is currently forcing the cautious expansion of scientific language. But until that happens, science remains suspended in a very specific kind of uncertainty, not ignorance, not absence of data, but incomplete resolution. The evidence is strong enough to prevent dismissal, but not strong enough to allow confirmation. That is precisely the space where phrases like reasonable hypothesis emerge. And what makes this moment particularly unusual in planetary science is that Mars is not providing just one category of signal. It is providing multiple, independent systems that all point toward a planet that was once chemically active, hydrologically stable, and potentially capable of supporting prebiotic or biological processes. Mars had water systems that behaved like Earth's rivers and oceans. It has minerals that form only in long-term warm rainfall conditions. It preserves organic molecules that resist simple abiotic explanation at observed concentrations. And it may have internal geological activity still shaping its rotation and mantle dynamics today. That combination is rare, not because each piece is individually unprecedented, but because they converge on the same environmental conditions: warmth, stability, water, chemistry, time. On Earth, that combination does not remain biologically neutral for long, which is why, even in the absence of confirmation, the scientific posture is shifting, carefully, quietly, incrementally, not toward declaring life, but toward admitting that the question is no longer speculative in the abstract sense, it is empirical. And while researchers continue refining models of ancient Mars, another discovery adds a final layer of complexity, one that feels almost symbolic in its timing. Because while we are debating whether Mars once supported lifelike chemistry, while we are reconstructing oceans and rainfall systems and sedimentary basins from billions of years ago, something unexpected is happening in the thin present-day atmosphere of Mars. Mars is producing electrical activity. Lightning-like discharges have been detected in dust devils and atmospheric disturbances, recorded indirectly through plasma wave signatures and acoustic sensing. These are not Earth-like thunderstorms, but triboelectric discharges, static electricity generated by dust particles colliding in the thin, dry atmosphere. It is a reminder that Mars is not just a fossilized world of the past. It is still an active system, still capable of energy transfer, still changing chemically in real time. And that brings everything full circle, because the same planet that may now only generate sparks in dust storms was once, according to the growing body of evidence, a world of rivers, oceans, rainfall, and possibly the chemistry of life itself. And the language scientists are now using carefully, cautiously, deliberately, is beginning to reflect that uncomfortable possibility. Not that life existed, but that, under the right interpretation of the evidence we already have, it is no longer unreasonable to think that it might have. Part 10. Lightning confirmed on Mars. Let's step away from ancient Mars for a moment. Not the river deltas, not the oceans, not the long-lost climate that may or may not have resembled Earth's early history. Let's talk about something happening right now on Mars. Today, in the present tense, on a planet we still instinctively think of as dead, because Mars is not silent. In 2015, NASA's MAVEN spacecraft, a mission designed specifically to study how Mars lost its atmosphere, was quietly collecting plasma wave data while orbiting the planet. Its instruments are not cameras or weather sensors. They are sensitive detectors of electromagnetic fluctuations, the kind of subtle signals that reveal how charged particles move through space environments. Most of what MAVEN sees is expected noise, solar wind interactions, background plasma oscillations, instrument artifacts that scientists spend years learning to filter out. But buried in that dataset, researchers later identified something that did not belong. It was brief, it was sharp, and it had a very specific structure that immediately stood out to physicists who study planetary electricity. It was a Whistler wave. That word sounds almost poetic, but in space physics it has a very precise meaning. A Whistler wave is a type of electromagnetic signal produced when a powerful electrical discharge, most commonly lightning, injects energy into a planet's electromagnetic environment. That energy does not travel in a straight line. It propagates along magnetic field lines, dispersing as it moves, with higher frequencies traveling faster than lower ones. The result, when converted into audio, is a descending tone that sounds like a whistle falling in pitch. It is one of the most recognizable signatures of lightning activity in planetary science. On Earth, whistlers are everywhere. Every lightning strike produces them. They travel through the ionosphere, bounce along magnetic field lines, and can even be detected thousands of kilometers away from their origin. They are so reliable that they are used as indirect tracers of storm activity, even when the lightning itself is hidden from view. So when MAVEN detected a Whistler-like signal at Mars, the implication was immediate and uncomfortable. Because whistlers do not exist in isolation, they require a source, and that source is almost always electrical discharge in an atmosphere, in other words, lightning. But the conclusion was not accepted immediately. It could not be. Mars is not Earth. Its environment complicates every assumption we normally make about planetary electricity. For one thing, Mars does not have a global magnetic field. Earth's magnetic field is generated by a dynamo in its molten core, forming a protective planet-wide structure that shapes how charged particles move through space. It channels solar wind, protects the atmosphere, and provides stable pathways for electromagnetic waves like whistlers to travel. Mars lost that global field billions of years ago. What remains instead are scattered remnants, patches of crustal magnetism, fossilized signatures of an ancient dynamo. These regions are irregularly distributed across the planet, strongest in some areas and absent in others. They behave less like a unified magnetic field and more like a fractured mosaic, localized zones of magnetic influence embedded in an otherwise weak electromagnetic environment. Imagine trying to transmit a radio signal not through a structured network, but through a landscape of broken antennas, each oriented differently, each affecting the signal in unpredictable ways. That is the environment MAVEN is working with. So when the Whistler signal appeared, scientists had to ask a difficult question. Was this truly a planetary atmospheric phenomenon, or was it a distortion artifact created by Mars's chaotic magnetic landscape? The answer came slowly, through repeated analysis. The signal structure was too coherent to dismiss. Its frequency dispersion followed the exact pattern expected from a wave propagating through a magnetized plasma. Its timing matched conditions where charged particle activity was elevated, and most importantly, its characteristics aligned with what you would expect if an electrical discharge had occurred somewhere in the Martian atmosphere, and the resulting electromagnetic ripple had travelled upward into space. Not proof of lightning in the Earth sense, but something very close in physical principle. A discharge event, an atmospheric spark, a moment where charge imbalance resolved violently enough to generate a planetary-scale electromagnetic signature. Lightning on Mars. But this is where things become more interesting and more subtle. Because Martian lightning, if we are to call it that, is not like terrestrial lightning. On Earth, lightning is driven by massive convective storm systems. Warm air rises, cold air sinks, ice particles collide inside towering clouds, and electrical charge separates over large vertical distances. This creates enormous potential differences, sometimes hundreds of millions of volts, that discharge in spectacular bolts stretching kilometers across the sky. Mars does not have that kind of atmosphere. Its air is thin, less than 1% of Earth's surface pressure. It cannot support the same towering cloud structures, it cannot sustain the same convective energy cycles, and yet it still manages to generate electrical activity. The difference lies in the mechanism. On Mars, the dominant driver is not water vapor and ice. It is dust. Fine, electrostatically active dust particles dominate the Martian surface and atmosphere. And when those particles are lifted into motion by wind, turbulence, or dust devils, they collide constantly. Each collision transfers tiny amounts of charge between grains. Individually, these charges are insignificant, but collectively, across billions of particles in motion, they build up into measurable electrical potential differences. This process is called triboelectric charging. It is the same mechanism that can make your clothes cling in a dry environment, or produce static shocks when you touch a metal surface. But on Mars, scaled up across kilometers of swirling dust columns, it becomes something far more dramatic. A dust devil on Mars is not just a wind phenomenon, it is an electrically active column of moving charge. And that is where Maven's Whistler detection begins to connect with something happening closer to the surface. Because while Maven was detecting electromagnetic signatures from orbit, another mission, NASA's Perseverance rover, was quietly sitting on the surface of Mars, equipped with one of the most unexpected instruments ever sent to another planet, a microphone. Originally intended to capture sound for engineering diagnostics and atmospheric studies, Perseverance's SuperCam microphone has provided something scientists did not fully anticipate: direct acoustic evidence of Martian environmental dynamics. And among those recordings, researchers identified something extraordinary. When dust devils pass directly over the rover, the microphone picks up a sequence of sharp, irregular crackling sounds, not wind noise, not mechanical vibration, electrical discharges, tiny bursts of static electricity releasing inside the dust column as particles collide and separate charge faster than it can be redistributed. In some cases, these discharges occur multiple times within a single dust devil event. The implication is subtle but profound. Mars is not just moving dust through its atmosphere, it is actively generating electrical energy in real time through mechanical motion alone. In total, Perseverance has recorded dozens of such events, each one representing a moment where the Martian atmosphere briefly behaves like an electrical system, rather than just a passive gas envelope. Taken together with Maven's orbital detection, the picture becomes difficult to ignore. Mars has electrical activity, not in the form of stable, Earth-like thunderstorms, not in the form of predictable weather systems, but in a more fragmented, more chaotic, and arguably more primitive form of atmospheric electricity. And once you accept that, another consequence follows. Because atmospheric electricity does not just produce light and sound, it drives chemistry. On Earth, lightning is one of the primary natural mechanisms for breaking molecular bonds and forming new compounds. It plays a role in nitrogen fixation, in atmospheric chemistry cycles, and in the generation of reactive chemical species that would otherwise not exist in the same quantities. On Mars, electrical discharges inside dust storms and dust devils could be doing something similar, but in a very different chemical environment. They may be breaking down methane. That detail matters. For years, methane fluctuations in the Martian atmosphere have been one of the most debated signals in planetary science. Methane is important because on Earth, a significant portion of it is produced biologically. Its presence on Mars raised the possibility of subsurface microbial activity or unknown geological processes releasing it intermittently. But methane is unstable. It does not last long under ultraviolet radiation, and if electrical discharges are occurring frequently enough in the Martian atmosphere, they could provide an additional destruction pathway, rapidly breaking methane apart before it accumulates to detectable levels. That creates a paradox. If methane is being detected intermittently, it may not simply be about production. It may also be about timing and destruction cycles, a system where methane is continuously produced, continuously destroyed, and only occasionally detectable when conditions briefly align. Which means the Martian atmosphere is not just chemically active, it is dynamically unstable, and that instability reframes everything we think we understand about present-day Mars. Because we often describe Mars as a static planet, a geological museum, a frozen world where all the interesting activity happened billions of years ago. But the combination of Maven's orbital plasma wave detection and Perseverance's ground-level electrical recordings tells a different story. Mars is still interacting with energy, still producing electrical phenomena, still capable of atmospheric processes that, while weaker and more fragmented than Earth's, are nonetheless real, measurable, and ongoing. And that realization creates a bridge between past and present. Because the same planet that once may have hosted rivers, oceans, rainfall, and long-term climate stability is not a completely inert remnant of that era. It is still active, just operating at a lower intensity state, a planet that has not fully shut down. And that becomes important when you connect it back to everything else we now know: the ancient oceans, the rainfall-driven minerals, the organic molecules trapped in mudstone, The possibility, still unresolved, that Mars once supported conditions favourable to life. Because now we're no longer just talking about a planet that used to be habitable. We're talking about a planet that may still be geophysically and chemically alive in its own reduced way. And somewhere between those two states, ancient habitability and present-day electrical activity, lies the real mystery of Mars. Not whether it once had water, not even whether it once had life, but whether the systems that made those conditions possible ever fully stopped, or whether deep down Mars is still running, slowly, quietly, and in ways we are only just beginning to detect. Part 11. Dust Devils, That Spark. Perseverance carries a microphone. On the surface, that does not sound like a serious scientific instrument. In the hierarchy of planetary exploration tools, a microphone feels almost decorative. It is easy to imagine it as a public outreach feature, something added so the public can hear Mars, a novelty layered on top of the real science hardware. Spectrometers, cameras, drill systems, sample caching tubes. But that assumption turns out to be wrong in a very important way. Because the microphone on Perseverance has done something subtle but profound. It has revealed that Mars is not just a silent world. It is an audible environment with structure, motion, and, unexpectedly, electrical activity embedded in its wind systems. Mars does not sound like Earth. It is quieter, thinner, more fragmented. Sound travels differently in its low-pressure atmosphere, arriving softer, delayed, and filtered through a medium that struggles to carry vibration. Wind does not roar there. It whispers, it fades, it dissolves. And yet, within that faint acoustic landscape, Perseverance has detected something that should not exist in a purely mechanical wind system. It has detected crackling, not the steady hiss of moving air, not the low-frequency rumble of pressure changes, but sharp, irregular staccato bursts of sound that resemble electrical discharge events, short, energetic impulses embedded within dust-driven airflow. Across multiple dust devil encounters, researchers identified a pattern. These crackling signals were not isolated anomalies. They were repeatable, spatially and temporally correlated with dust column passages. In total, the rover recorded 55 distinct electrical events associated with dust activity. 55. Not a statistical hint, not a borderline detection, a repeated phenomenon occurring under identifiable environmental conditions, and that is where the interpretation becomes unavoidable, because those signals are consistent with something very specific, electrostatic discharge inside Martian dust devils. The mechanism behind it is called triboelectric charging, and while the name sounds technical, the physics is deceptively simple. When two materials collide and separate, electrons can transfer from one to the other. This is something you have likely experienced personally. It is the reason a balloon rubbed against hair can stick to a wall. It is the reason you sometimes feel a static shock after walking across a carpet and touching a metal object. At small scales, it is a familiar annoyance. At planetary scales, it becomes something far more significant. On Mars, the dominant material in the atmosphere is dust. Fine, pervasive, electrostatically active particles are constantly being lifted, moved, and collided by wind systems. Inside a dust devil, this process becomes highly organized. The vortex acts as a sorting machine. Larger particles tend to remain lower in the column due to mass and inertia. Smaller particles are more easily lifted and carried upward toward the center and upper regions of the vortex. But these particles are not neutral after repeated collisions. They exchange charge. Smaller particles tend to accumulate negative charge. Larger particles tend to become more positive. As the dust devil spins, it does more than just mix particles. It separates them. It creates vertical charge stratification inside the vortex. And when charge separation becomes large enough, physics does what it always does when imbalance grows beyond a threshold. It resolves it. A discharge occurs, a sudden release of electrical energy, a microscopic spark, a localized breakdown of the insulating properties of the air, a crack. That crack is what Perseverance heard, and when you step back from the instrument-level detail and consider the planetary scale, the implications begin to expand rapidly. Dust devils on Mars are not rare, localized curiosities. They are one of the most common atmospheric features on the planet's surface. Orbital imaging has revealed vast networks of dust devil tracks etched across Martian terrain. Dark streaks carved where swirling vortices have removed or redistributed surface dust. These tracks are so abundant that in some regions they form intersecting patterns across entire landscapes. In other words, dust devils are not occasional events. They are a fundamental atmospheric process. And during certain seasons, Mars experiences even more extreme conditions, global and regional dust storms that inject enormous quantities of fine particulate material into the atmosphere. During these periods, suspended dust becomes so dense that sunlight is significantly reduced at the surface. The sky itself turns opaque. The entire planet becomes an active dust system. Now combine that environmental reality with Perseverance's local detection of electrical discharges. 55 events at a single site, across a limited observational window, at one location on an entire planet filled with similar dust activity. And a logical extrapolation begins to emerge, even if it is still probabilistic. If dust devils at one rover location can generate detectable electrical discharges, and dust devils occur across the planet in massive numbers, then Mars is likely not just occasionally electrically active, it may be continuously, globally electrically active at a low level. Not in the form of Earth-like thunderstorms, not in towering cumulonimbus systems or planet-spanning lightning networks, but in a fragmented, distributed and highly localized electrical environment embedded directly within its wind and dust dynamics. A kind of granular electricity spread across the planetary surface, and this is where the story begins to connect back to chemistry. Because electrical discharges in dusty atmospheres are not just acoustic or electromagnetic curiosities, they are chemical engines. On Earth, lightning is one of the most powerful natural drivers of atmospheric chemistry. It breaks nitrogen molecules apart, enabling the formation of reactive nitrogen compounds that are essential for life. It produces ozone. It generates radicals, highly reactive chemical species that rapidly recombine into new molecular structures. It reshapes atmospheric composition in measurable ways. Even small-scale electrical discharges can have disproportionate chemical effects in environments rich in particulates and reactive gases. Now transfer that concept to Mars. The Martian atmosphere is thin, yes, but it is also chemically active, with trace gases, oxidizing surface conditions, and a constant flux of dust interacting with ultraviolet radiation. In that environment, electrical discharges inside dust devils could be acting as localized chemical reactors. They may be breaking molecular bonds on the surface of dust grains. They may be generating reactive oxygen species. They may be oxidizing surface materials in ways that alter long-term geochemical signatures. And crucially, they may be interacting with one of the most debated molecules in Martian science: methane. Methane on Mars has been one of the most persistent scientific puzzles of the last 2 decades. Multiple instruments, both orbital and ground-based, have reported intermittent detections of methane in the Martian atmosphere. Sometimes it appears in spikes. Sometimes it seems to vanish. Sometimes it is detected at levels that are difficult to reconcile with expected atmospheric destruction rates. On Earth, methane is significant because a large portion of it is biologically produced. That does not mean methane automatically implies life elsewhere, but it does make it a molecule of intense interest in astrobiology. Any unexpected methane detection on another planet immediately raises questions about subsurface chemistry, geological processes, or biological activity. But methane is also fragile. Under ultraviolet radiation, it breaks down over relatively short timescales. That alone makes its persistence on Mars puzzling. And now, with the evidence of electrical activity inside dust systems, another destruction pathway enters the picture. Electrical discharges are extremely effective at breaking molecular bonds. They generate energetic electrons and reactive radicals capable of rapidly decomposing organic molecules. If dust devil electricity is widespread enough, it could provide a continuous planet-scale mechanism for methane destruction, not uniform destruction, not steady-state removal, but intermittent, spatially variable breakdown driven by atmospheric dynamics, and that creates a much more complex picture. Because if methane is being produced somewhere on Mars, whether biologically, geologically, or through subsurface chemical reactions, it may not accumulate in a stable way. Instead, it could be continuously injected into the atmosphere, then rapidly broken down by ultraviolet radiation and electrical discharge events in dust systems. That means the methane signal we observe is not just a measure of production. It is the result of a dynamic equilibrium between creation and destruction, and that equilibrium may fluctuate depending on dust activity, atmospheric circulation, seasonal cycles, and even local weather conditions. Which brings everything back to Perseverance's microphone. A device designed to capture sound has unintentionally revealed something much more important than acoustic novelty. It has provided direct evidence that Mars is not just a passive environment where wind moves dust across a static surface. It is a coupled physical-chemical system where mechanical motion, electrical energy, and atmospheric chemistry are linked in real time. Dust moves, charge builds, electricity discharges, chemistry changes, and all of it is happening right now on a planet we still tend to describe as geologically dead. But Mars is not fully dead in the way that word implies. It is active, just at a different scale and intensity than Earth. Its systems are weaker, thinner, more fragmented, but they are still operating, still interacting, still producing measurable energy transfers across physical domains, and that realization changes how we interpret everything else we have found there. Because if the present-day Mars atmosphere is electrically active, even intermittently, then the planet is not just preserving its past in rock and sediment, it is also continuously modifying its surface and atmospheric chemistry in the present. That means any organic molecules we find in ancient sediments, any potential biosignatures, any chemical remnants of past environments, have not simply been sitting untouched for billions of years. They may have been slowly altered, oxidized, or destroyed by a planet that is still, even now, capable of generating sparks inside its own storms. And that brings the story full circle. Because Mars is often framed as a planet frozen in time, a geological museum preserving the memory of a warmer, wetter era. But the reality emerging from both MAVEN's orbital data and Perseverance's surface recordings is more complicated. Mars is not frozen. It is still running at low power, a planet where wind still moves dust, dust still generates electricity, and electricity still reshapes chemistry in ways we're only beginning to understand. And somewhere inside that system, between ancient oceans and modern dust devils, lies a continuity we're only now starting to see clearly. Mars was never fully turned off. It only changed states. Part 12. The methane mystery gets complicated. Methane should not be on Mars. At least not in the way we are seeing it. Because under the known chemistry of the Martian atmosphere, methane is fundamentally unstable. The planet is bathed in ultraviolet radiation that relentlessly breaks molecular bonds. Unlike Earth, Mars does not have a thick ozone layer to shield its lower atmosphere. It does not have a dense protective blanket of air to slow down photochemical reactions. Any methane molecule released into the Martian sky is exposed almost immediately to high-energy photons that begin dismantling it. The expected lifetime of methane in that environment is short, on the order of a few hundred years at most, and possibly much less depending on altitude and atmospheric conditions. In planetary terms, that is nothing. A blink. A molecule released today should not still be detectable thousands of years later, and yet spacecraft and telescopes have repeatedly detected methane in the Martian atmosphere. Not in a steady, predictable way, not as a uniform global signal, but as sporadic, localized spikes, brief increases in concentration that appear, vanish, and reappear in different regions and at different times. Sometimes orbiters detect elevated methane levels. Sometimes ground-based instruments report seasonal fluctuations, and sometimes missions designed to confirm earlier detections fail to find it at all. It is inconsistent, fragmented, elusive, and that inconsistency is precisely what makes it so scientifically compelling. Because methane, in a planetary atmosphere, is not just another trace gas. It is a signal that demands explanation. On Earth, methane is overwhelmingly biological in origin. Methanogenic archaea, microorganisms that thrive in oxygen-free environments, produce methane as a metabolic byproduct. These organisms live in swamps, wetlands, sediments, and the digestive systems of animals. They are ancient, widespread, and remarkably efficient chemical factories. If life exists, or ever existed, beneath the Martian surface in protected niches where liquid water could persist, then methane becomes a natural consequence of biology. Microbial ecosystems could, in principle, produce methane that slowly migrates upward through cracks in the crust, eventually leaking into the atmosphere. That has been one of the most enduring hopes in Mars science, that methane spikes might represent a modern biological signature, not just a geological relic. But Mars never makes things that simple, because methane does not require life. There are abiotic pathways capable of producing it. One of the most studied is a process called serpentinization. This occurs when water interacts with iron-rich minerals in ultramafic rocks. The chemical reaction produces hydrogen, and under certain conditions that hydrogen can combine with carbon-bearing compounds to form methane. This process happens without biology, deep within planetary crusts where water and rock interact over long time scales. There is also the contribution of meteoritic material. Organic compounds delivered by meteorites can be broken down by ultraviolet radiation on the surface, releasing small amounts of methane or methane precursors into the atmosphere. In other words, even a lifeless Mars would not be chemically inert. It would still produce trace gases through slow geological and photochemical processes. So the methane problem has always been ambiguous. Two competing explanations, one biological, one geological, both plausible in isolation, neither proven, neither ruled out. And the difficulty is not just conceptual, it is observational. The concentrations involved are extremely small, measured in parts per billion. Detecting methane at that level requires extraordinary precision, and even then the readings are influenced by atmospheric circulation, seasonal variation, dust activity, and instrument sensitivity. Which means every detection comes with uncertainty built in. Every non-detection does too. For years, the scientific community has been left with a frustrating pattern. Signals that appear real, but refuse to behave consistently enough to confirm a stable source. And now, into that already complex system, a new variable has emerged: electrical activity in Martian dust systems. At first glance, this might seem unrelated to methane entirely, but the connection becomes important when you consider what electrical discharges do to atmospheric chemistry. Lightning on Earth is not just a visual phenomenon, it is a chemical engine. The energy released in a discharge is sufficient to break stable molecular bonds, producing highly reactive species such as free radicals and ions. These reactive fragments go on to participate in secondary reactions that alter atmospheric composition. Nitrogen oxides, ozone, and other transient compounds are all products of electrical energy injected into the atmosphere. Now consider Mars. The recent evidence from both orbital plasma wave data and surface-level acoustic recordings suggests that Mars is not electrically inert. It may not have Earth-like thunderstorms, but it does appear to generate localized electrostatic discharges, particularly within dust storms and dust devils. These discharges are not massive planet-wide lightning bolts. They are smaller, more frequent, and embedded within the constant movement of fine particulate matter across the surface. But chemically, they still matter, because even small-scale electrical discharges can break molecular bonds. And methane is not a robust molecule in energetic environments. It is fragile. It oxidizes easily under reactive conditions. It can be broken down by ultraviolet radiation, by interaction with reactive oxygen species, and potentially by electron-driven processes generated during electrical discharge events, which introduces a critical complication into the methane debate. If Mars has widespread intermittent electrical activity embedded in its dust systems, then methane is not just being produced and slowly destroyed by sunlight. It is also being actively processed by the planet's weather system itself. That changes the entire interpretation of atmospheric measurements. Under the older framework, low methane concentrations implied low production rates. If you detect only a few parts per billion, then the assumption is that not much methane is being generated anywhere on the planet. But under a revised framework that includes active electrical destruction, that assumption breaks down. Because now there are two competing processes operating simultaneously, one producing methane, one destroying it. And the methane we detect is not a direct measurement of production. It is the net result of a dynamic equilibrium between creation and destruction. This is a crucial shift in thinking. If destruction rates are higher than previously estimated, if dust-driven electrical discharges are continuously breaking down methane in localized regions, then the observed atmospheric concentration could remain low even if production rates are relatively high. In other words, Mars could be producing significantly more methane than we think, but we're only seeing the fraction that survives long enough to be measured before being destroyed. That possibility completely reframes the scientific problem. It means methane spikes are not simple indicators of production events. They are snapshots of a rapidly fluctuating system where gases are being injected, transported, and chemically erased on short timescales. And that leads to a deeper implication. Mars is not chemically static. It is chemically active and cycling. Energy is being injected into the system from multiple sources: ultraviolet radiation from the sun, mechanical energy from wind-driven dust movement, and electrical energy from triboelectric charging inside dust storms. Each of these inputs drives reactions. Each of them modifies atmospheric composition. Each of them contributes to a system that is constantly reshaping itself at a microscopic level, and that activity does not stop at the atmosphere. Because methane is only one piece of a much larger question. What is happening beneath the surface? For methane to appear in the atmosphere at all, there must be a source. Something must be producing it at depth, where it can be shielded from immediate destruction long enough to accumulate and migrate upward. That source could be geological. It could be chemical reactions occurring in water-bearing rock formations. It could be serpentinization deep in the crust, slowly releasing hydrogen and methane over time. It could be trapped reservoirs of ancient organic material being broken down by heat and pressure. Or it could be biological. Microbial ecosystems, if they exist today on Mars, would almost certainly be subsurface, protected from radiation, insulated by rock, potentially sustained by chemical gradients rather than sunlight. In such environments, methane would be a natural metabolic byproduct, slowly diffusing upward into fractures and pores in the crust. We do not know which scenario is correct, but we do know that methane is being produced somewhere, and we now have evidence that methane is also being destroyed more actively than previously understood. So the system is not a simple source and detection model. It is a balancing act between hidden production and active atmospheric destruction, and that balance may be far more unstable than we thought. Because if destruction mechanisms, ultraviolet photochemistry plus electrical discharge chemistry, are stronger than assumed, then either production must be higher to compensate, or methane would not appear at all. There is no middle ground in that equation. Which forces a difficult conclusion. The methane system on Mars is telling us that something is active beneath the surface, even if we cannot yet determine what that something is. And that brings us to the larger realization emerging across all recent Mars data. The planet is not passive. It is not a frozen archive. It is not simply a dead world preserving the memory of a warmer past. It is a system still receiving energy, still redistributing that energy, and still responding to it through chemistry, electricity, and geology. And that activity does not end with the atmosphere, because even deeper than the dust, deeper than the rocks, deeper than the chemical cycles we can measure from orbit or rover instruments, there is another signal, subtle, long-term, and profoundly revealing. Mars is still moving. Part 13. Mars is speeding up. Here is something that sounds like it should not be true, yet it is. Mars is spinning faster, not in any dramatic, observable way, not in a way that would ever be visible to the human eye, or even noticeable across human history. This is not a planet suddenly changing behavior or entering a new phase of instability. It is something far more subtle, almost invisible in its scale, and yet profoundly important when you understand what it implies. Mars is shortening the length of its day by roughly 70 microseconds per year. That is 70 millionths of a second removed from each full rotation of the planet, accumulating steadily, year after year, without interruption. On a human scale, that number feels meaningless. It is far too small to matter in daily life, and far too slow to notice even across generations. But planets do not operate on human timeframes. They operate on physical constraints, conservation laws, and internal structures that evolve over millions to billions of years. And in that context, even a change this small becomes a signal that something deeper is shifting inside the planet. We know this because of one of the most elegant long baseline experiments ever conducted in planetary science. In 1976, the Viking landers arrived on Mars and became fixed reference points on another world. They transmitted radio signals back to Earth with precise timing, allowing scientists to measure the planet's rotation through Doppler shifts in those signals. At the time, this was a way to establish a baseline understanding of Mars as a rotating body. But what it actually created was something far more valuable, a historical anchor point. Decades later, NASA's InSight lander performed a similar function using its RISE instrument, which tracked extremely precise radio communications between Mars and Earth. Unlike Viking, which provided a snapshot, InSight allowed scientists to measure subtle changes in rotation over time with far greater precision. When researchers compared the Viking data from the 1970s with InSight measurements taken roughly 40 years later, they found something unexpected. Mars was not rotating at the same rate. It was spinning slightly faster. The difference is extremely small, but consistent. And consistency is what transforms noise into physics. The measured acceleration corresponds to about 70 microseconds per year. That means each Martian day is becoming fractionally shorter over time, not because of external forces acting on the planet, but because of something happening inside it. To understand why this matters, it helps to use a simple analogy from classical physics. A rotating object conserves angular momentum. That means if nothing external is adding or removing torque, its total rotational energy remains constant. But how that energy is distributed depends on the object's moment of inertia, which is determined by how mass is arranged relative to the axis of rotation. This is the same principle that explains why a figure skater spins faster when pulling their arms inward. They are not gaining energy, they are redistributing mass closer to their rotational axis, which reduces their moment of inertia and increases their spin rate. Mars appears to be doing something similar, but on a planetary scale. The acceleration in rotation suggests that mass inside the planet is gradually shifting inward, closer to the axis of rotation. That does not happen randomly. The only known mechanism capable of producing such a long-term redistribution of mass inside a rocky planet is mantle convection. This is the slow movement of material within a planet's interior, driven by heat. Hot rock deep inside the mantle becomes buoyant and rises, while cooler, denser material sinks. Over time, this creates circulation patterns that can persist for millions of years. These flows are not fast like atmospheric storms. They are geological currents, moving so slowly that they are invisible on human timescales, yet powerful enough to reshape an entire planet's internal structure. The implication is profound. Mars is not a fully frozen inert sphere of rock. It is not a dead planet in the strict geological sense. It still retains enough internal heat to drive convection in its mantle. That heat is a remnant of planetary formation, radioactive decay, and slow cooling over billions of years. And although Mars has lost much of its early geologic vigour, it has not completely shut down. Something inside it is still moving, and the region where this internal activity appears most significant is not random. It is concentrated in a specific geological province that has already appeared repeatedly throughout the broader story of Mars, a region responsible for shaping much of the planet's surface and possibly influencing its internal dynamics. Tharsis. Tharsis is one of the most extraordinary geological structures in the solar system. It is a vast volcanic plateau that spans thousands of kilometers and contains some of the largest volcanoes ever discovered, including Olympus Mons, a shield volcano so large it dwarfs anything on Earth. The entire region is so massive that it physically deforms the shape of Mars, creating a planetary bulge visible even from orbit. For decades, Tharsis has been understood primarily as an ancient volcanic province, a relic of a more active Martian past when magma rose repeatedly to the surface. But newer interpretations suggest that Tharsis may not be entirely inactive. Instead, it may sit above a long-lived mantle plume, a column of rising hot material deep within the planet that continues to influence internal structure even today. On Earth, mantle plumes are responsible for hotspot volcanism like Hawaii, where volcanic activity persists far from tectonic boundaries. On Mars, the Tharsis plume appears to be far larger in scale and potentially more influential in shaping the planet's internal mass distribution. And that is where the rotation data becomes significant again. If material beneath Tharsis is slowly shifting in a way that redistributes mass closer to Mars's rotational axis, even slightly, it would naturally lead to a measurable increase in spin rate. In that sense, the 70 microseconds per year is not just a number. It is a fingerprint of internal motion. What makes this even more intriguing is that Mars has long been considered geologically dead in popular imagination. A frozen world that cooled quickly after formation, lost its magnetic field, and became inactive billions of years ago. But that model is increasingly difficult to reconcile with multiple independent lines of evidence. We now know that Mars has active atmospheric electricity generated by dust storms. We know that its surface chemistry is still being modified by ultraviolet radiation and electrostatic discharges. We know that methane appears and disappears in patterns that suggest ongoing production and destruction processes. We also know that ancient Mars once had rivers, lakes, rainfall, and possibly long-lived oceans. And now we have evidence that its interior is still slowly adjusting, still moving, still redistributing mass. When all of these layers are considered together, a different picture begins to emerge. Mars is not a static relic. It is not a planet locked in geological stasis. It is a system operating at very low energy, but still operating nonetheless. Its atmosphere is active, its surface is reactive, and its interior is dynamic. The rotation acceleration is particularly important because it ties the entire system together. It suggests that what we are seeing on the surface and in the atmosphere is not isolated phenomena. They are all expressions of a planet that still has internal energy driving slow but continuous change. And Tharsis may be the key to understanding that engine. It is both a remnant of ancient volcanism and a potential indicator of ongoing mantle processes. It is the place where Mars built its largest mountains, and possibly the place where its internal heat still finds expression today, albeit in ways that are no longer explosive or visible at the surface. What this ultimately means is that Mars has not completed its geological story. It has slowed dramatically, lost its early Earth-like conditions, and transitioned into a cold, thin, and arid state. But it has not fully shut down. The engine still runs, just at a fraction of its former power, and that realization forces a re-evaluation of what dead actually means in planetary science. Because Mars is not dead in the way a cold rock is dead. It is not inert. It is not static. It is still evolving, still adjusting, still responding to internal and external forces. It is a planet in deep slow motion, and 70 microseconds per year is how we know it is still alive. Part 14. The Hidden Engine Beneath Tharsis. The Tharsis region is, by almost any geological standard, the most extreme landscape feature in the entire solar system. It is not just a volcano field or a collection of mountains. It is a planetary-scale deformation of Mars itself, a vast, elevated plateau that stretches roughly the size of North America and rises up to 10 kilometers above the surrounding terrain. Sitting on top of this elevated bulge are 4 massive shield volcanoes, Ascraeus Mons, Pavonis Mons, Arsia Mons, and the most famous of them all, Olympus Mons. Each of these structures is enormous in its own right, but Olympus Mons in particular is almost incomprehensible when viewed through an Earth-based frame of reference. It stands approximately 22 kilometers high, making it nearly 2.5 times taller than Mount Everest. Its base is so wide that if it were placed on Earth, it would not resemble a mountain so much as a geological continent, sprawling across an area large enough to cover most of France. For a long time, planetary scientists treated Tharsis as a relic of Mars's volcanic past. It was seen as a monument to a time when the planet was more geologically active, more thermally energetic, and more dynamic in its interior processes. There was no question that it had been active. The lava flow records, crater counts, and surface dating techniques all indicate that volcanic activity in the Tharsis region persisted for billions of years. Some flows are geologically recent, possibly only a few 100 million years old, which in planetary terms is relatively young. But the dominant interpretation for decades was that this was a dead system, a long-faded volcanic engine that once reshaped the planet, but had since cooled, hardened, and shut down. The heat source that built Tharsis, it was assumed, had exhausted itself. The mantle beneath it had solidified. Mars, in this view, was finished. But the rotation data we now have forces a more uncomfortable interpretation. When geophysicists attempted to explain why Mars is spinning faster today than it was during the Viking era, they did not arrive at surface processes or atmospheric effects. The numbers are too consistent, too long-term, and too globally integrated for wind or seasonal mass redistribution to explain them. Instead, the models converged on something much deeper, a change in the planet's internal mass distribution. And the only process capable of producing that kind of slow, planet-wide shift is mantle convection. More specifically, the models point toward a mantle plume beneath Tharsis. A mantle plume is a column of anomalously hot, buoyant material rising from deep within a planet's interior, typically originating near the boundary between the core and the mantle. As this hot material rises, it carries energy upward and redistributes mass within the planet. On Earth, mantle plumes are responsible for hotspot volcanism, the most famous example being the Hawaiian island chain. In that case, a stationary plume pushes upward while the tectonic plate above it moves, creating a linear trail of volcanic islands that record the motion of the crust over the plume. Mars, however, does not have plate tectonics. Its outer shell is a single, rigid lithosphere. That means any mantle plume beneath the surface would not be dragged across the planet by moving plates. It would remain fixed relative to the crust, continuously feeding heat into the same region for potentially billions of years. This is precisely the kind of long-lived stationary heat source that could construct a volcanic province on the scale of Tharsis, gradually building massive shield volcanoes in a single clustered region over immense spans of time. If such a plume exists, and if it is still active today, then it changes the entire interpretation of Mars's interior state. Because an active mantle plume means the planet is not fully cooled. It means there is still enough thermal energy trapped inside Mars to drive slow convection currents in the mantle. And those currents, even if extremely weak compared to Earth's, are sufficient to alter how mass is distributed inside the planet. That is where the rotation anomaly becomes relevant again. As hot material rises beneath Tharsis, it displaces cooler, denser material and shifts mass distribution within the mantle. Depending on the geometry of that flow, it can move mass closer to the planet's rotational axis, and when mass moves closer to the axis, the planet's moment of inertia decreases. The result, under conservation of angular momentum, is an increase in rotation speed. The skater pulls their arms inward. The planet spins slightly faster. 70 microseconds per year is not just a number in that context. It becomes a measurable signature of internal redistribution, a slow-motion fingerprint of a planet still undergoing structural adjustment deep within its interior. The implications of this are significant because they overturn the long-held assumption that Mars is geologically dead. Instead of a frozen interior, what we're seeing is a system operating at extremely low energy, but still operating nonetheless. The mantle is not frozen solid. It is creeping, slowly convecting, still transporting heat from deep within the planet toward the surface. The engine has not stopped. It has simply fallen into a long, low-power state, and that has consequences that extend beyond rotation. If a mantle plume beneath Tharsis is still active, it may also be influencing the planet's atmosphere in subtle but important ways. Volcanic systems, even dormant or low-activity ones, can release gases trapped in the interior of a planet. On Mars, that would primarily involve carbon dioxide, water vapour, sulfur compounds, and trace gases locked in crustal reservoirs. These emissions would not resemble explosive eruptions like those seen in Earth's geologically active zones. Instead, they would likely be diffuse, slow seepage through fractures in the crust, occurring over long timescales. But on a planet with an atmosphere as thin as Mars's, even small additions of gas can have disproportionate effects. A slight increase in greenhouse gases, even at trace levels, can influence local temperature gradients, atmospheric circulation patterns, and seasonal variability. Over geological time, these small contributions can accumulate into measurable atmospheric evolution. This raises an important possibility. Mars's atmosphere may not be entirely the passive remnant of an ancient loss process. It may still be influenced, however subtly, by internal outgassing. More speculatively, the presence of a heat source beneath Tharsis opens another possibility that intersects with one of the most important questions in planetary science: the existence of subsurface liquid water. Orbital radar data has hinted at layered subsurface structures in certain Martian regions that are consistent with the presence of ice, brines, or possibly even transient liquid water under specific conditions. If heat from a mantle plume is present beneath Tharsis, it could create localized thermal environments where subsurface ice is partially melted or maintained in a liquid state, particularly if mixed with salts that lower the freezing point of water. Such environments, if they exist, would be deeply buried, shielded from surface radiation, and thermally insulated by layers of rock and regolith. They would be dark, stable, and chemically active over long timescales. On Earth, analogous environments exist deep underground and beneath polar ice sheets, where microbial ecosystems thrive independently of sunlight, sustained entirely by chemical energy gradients and geothermal heat. If similar environments exist on Mars, they would represent one of the most important astrobiological targets in the solar system. Not because they guarantee life, but because they provide the combination of conditions that, on Earth, consistently support microbial ecosystems: stable liquid water, chemical energy, geological insulation, and time. Time is the critical factor. Because even if life never originated on Mars, environments like these could persist long enough to allow complex prebiotic chemistry or transient biological systems to emerge, evolve, or persist in isolated niches. And that brings the interpretation of Tharsis full circle. What was once thought to be a frozen relic of ancient volcanism now appears to be part of a deeper, still active system. A system that connects the interior heat of Mars to its surface chemistry, atmospheric evolution, and possibly even subsurface habitability. This is why the rotation data matters beyond its numerical precision. It is not just telling us that Mars is spinning slightly faster. It is telling us that the internal structure of the planet is still adjusting, still responding, still evolving in response to heat that has not yet fully escaped from its interior. Mars, in this sense, is not a static object that cooled and died. It is a system in slow thermal decline, still actively redistributing the energy it has left. And when you connect that internal activity to everything else we now know, the dust-driven electrical chemistry of the atmosphere, the methane cycles that refuse to stabilize, the evidence for ancient oceans and long-lived rainfall, the preserved organic molecules locked in ancient sediments, a coherent picture begins to form. Mars is not a collection of disconnected anomalies. It is a layered system where each component still interacts with the others, even at extremely low energy levels. The atmosphere still responds to solar radiation and dust activity. The surface still responds to wind, chemistry, and electrostatic discharge. The interior still responds to residual heat through mantle convection. And Tharsis sits at the centre of that system as both a geological monument to the past and a potential indicator of present-day internal motion. Which leads to the most important realization of all. Mars is not a planet that stopped. It is a planet that slowed down so dramatically that we almost mistook its ongoing activity for silence. But the signals are still there, in its rotation, in its chemistry, in its dust, and in the slow, persistent movement of rock deep beneath Tharsis, where the planet's last remaining heat continues to rise, fold, and reshape everything above it. Mars is not dead. It is still running, just at a speed we're only now learning how to measure. Part 15, the final reframe. Let us put it all together. In the first act of this story, we found kaolinite in Jezero crater, a mineral that requires millions of years of rainfall to form. That single rock told us that Mars had weather. Not just water, weather, clouds, rain, atmospheric pressure, temperature cycles, a planet with a sky that did something. In the second act, we followed the water from Jezero outward and discovered that Mars's rivers were not flowing into ponds. They were flowing into an ocean, 14 million square kilometres, shorelines at consistent elevations across an entire hemisphere, wave-modified deposits, a body of water large enough and persistent enough to require a planetary-scale hydrological cycle to maintain. In the third act, we opened the rocks and found chemistry that does not have a comfortable explanation. Chain-length hydrocarbons in ancient mudstone, at concentrations that no known abiotic process can fully account for, preserved in exactly the kind of environment where biological chemistry operates on Earth. Not proof, but an accumulation of coincidences that grows harder to dismiss with every new analysis. In the fourth act, we discovered that Mars is not chemically inert even today. Lightning crackles inside dust devils. Electrical discharges sweep across the surface during dust storms. Methane appears and disappears in patterns that suggest active production and active destruction happening simultaneously. The atmosphere is not a fossil, it is a reactive system. And in this final act, we learned that even the planet's interior is still in motion. A mantle plume beneath Tharsis, the largest volcanic province in the solar system, is actively redistributing mass inside the planet, speeding up its rotation by 70 microseconds a year. Mars still has an engine. It is not roaring, but it is running. So what is Mars? It is not the dead planet we were told about in school. It is not the cold, dry, rust-coloured husk that sits in our imagination as the solar system's most photogenic corpse. Mars is a planet that had rain, that had oceans, that had organic chemistry complex enough to make astrobiologists lose sleep, that still has atmospheric electricity, chemical cycling, and geological activity in its interior. Mars did not die. Mars changed state. The way a fire does not die when it becomes embers. The way a river does not die when it goes underground. The system slowed. The atmosphere thinned. The oceans froze and then sublimated away. The volcanoes quieted. but the underlying processes, the heat, the chemistry, the physics that made Mars a living world never fully stopped. They dropped below the threshold of visibility, below the threshold of easy detection, but not below the threshold of existence. And this is where the story stops being about Mars and starts being about us. Because what Mars shows us is that planetary habitability is not a switch, it is a dial. Earth's dial is turned up high right now. Mars's dial is turned way down, but it is not at zero. And 3.5 billion years ago it may have been turned up to a setting not so different from our own. We're reconstructing this history from fragments, a few rovers, a few orbiters, a handful of landing sites on a planet with a surface area nearly equal to Earth's total land area. We have sampled less than 1/1000th of 1% of Mars's surface. The story we're telling is not the complete story. It is the story visible from the tiny keyhole we've managed to peer through so far. And what we see through that keyhole is not a dead world. It is a world that once had everything we associate with the preconditions for life, and that still has more activity, more chemistry, more geological restlessness than we ever gave it credit for. The old narrative was simple. Mars was born, briefly flickered, and died. The new narrative is more complicated and more honest. Mars was born. It flourished in ways we're only beginning to understand. It changed, and it is still changing. We did not find a dead planet. We found one that never fully turned off. What if we are the interruption? There is a strange irony sitting on the surface of Mars right now, and it does not involve geology or chemistry. It involves a collection of small metal tubes, about the size of a whiteboard marker, carefully sealed and deposited in the dirt of Jezero crater by Perseverance. Those tubes contain rock and soil samples, the most scientifically valuable material ever collected off Earth, and they are stranded. NASA's Mars sample return mission was supposed to pick them up. A lander would descend, a small rocket would launch the samples into Mars orbit, a European spacecraft would catch them, and they would be flown back to Earth for laboratory analysis. It was the most ambitious interplanetary logistics chain ever conceived, and it was effectively shelved due to ballooning costs and engineering challenges that pushed the price tag past $10 billion and the timeline into the late 2030s. Those samples contain the answer. Maybe not the definitive case-closed answer to whether Mars ever hosted life, but almost certainly a transformative answer, the kind that comes when you take material out of a rover's limited onboard oven and put it under a mass spectrometer that fills an entire room, when you can run 1,000 tests instead of 3, when you can check for contamination with a certainty that no spacecraft instrument can match. China's Tianwen-3 mission is the current best hope for an independent retrieval. If it launches on schedule in the late 2020s and succeeds, a significant if, given the difficulty of the engineering, it could return Martian samples to Earth before 2035. The race to answer the oldest question in science may end up being decided not by which country has the best science, but by which one can afford the rocket. And in the meantime, humanity sits in a peculiar position. We know more about Mars than we have ever known. We know it had rain. We know it had oceans. We know it had complex organic chemistry and environments that match the preconditions for life. We know it is still geologically and chemically active. And we are closer than we have ever been to being able to answer the question that all of this evidence is circling around. Did Mars ever produce life? But we cannot answer it yet. The data is locked in tubes on the ground of another planet, or buried in rocks we have not yet drilled, or encoded in atmospheric measurements we have not yet made. The story of Mars is not over. It is not a solved case. It is an investigation mid-stride, and we are the generation that opened the file but has not yet reached the last page. Maybe that is the most honest way to leave this, not with a conclusion, not with a verdict, but with the recognition that we are standing in the middle of the most important scientific investigation our species has ever conducted, and we do not yet know how it ends. Mars is still out there, spinning slightly faster every year, crackling with electricity, hiding chemistry in its rocks that we cannot quite explain, holding its secrets loosely enough that we can see their outlines, tightly enough that we cannot yet read them clearly. We did not arrive at a dead world and confirm what we expected. We arrived at a world that challenged everything we thought we knew, and we're only a few chapters in. The question is not whether Mars has more to tell us. The question is whether we'll be patient enough and bold enough to listen.